My name is Patrick Schäfer, and I'm going to present our joint work with Ulf Leser called Motiveless Simple and Accurate Detection of Motives in Time Series, which was accepted at VLDB 2023. What are time series? Time series are everywhere. Whenever we record data over time, we see a time series. Depicted is a time series of an audio file. Other examples include sensor data, medical data like ECG and EEG signals, stock data, financial data, biological processes, motion data, video, and like depicted music. When we have a time series, we can extract subsequences of a fixed length W. We can think of each of these subsequences as points in W-dimensional space. In total, there are n minus W plus 1 subsequences given a time series of length n. So each of these dots represents one subsequence. The motive pair is now the pair of subsequences that are closest to each other, depicted in blue. But if we look at time series, rarely subsequences occur only in pairs, or interesting motives occur only in pairs. So we're looking at motive sets, which are frequent, approximately repeated patterns of a time series. Depicted are, for example, some subsequences of a motive of a longer sequence. There are many definitions of motive sets in the literature. Each definition can be mapped to a geometric shape, also called hypersphere. All of these have in common that they use a distance threshold r, which is a crucial input parameter. So depicted is a time series, and we can look at the geometric shape again of different definitions. As introduced, the pair motive is simply the pair of subsequences that are closest together. To move from pairs to sets, Valmont is one possibility. It uses the pair motive as seeds and searches for a hypersphere of radius r around each of these seed points. Another common definition is that of k-motives. Here again, we have an existing subsequence and look for all subsequences within a radius of r, which basically equals a circular shape. We can relax the constraint that we only use existing subsequences as centers of this hypersphere to using any point in space and doing a radius r search. As you can see, we may find more subsequences within radius r if we relax this constraint. Interestingly, there's another definition based on pairwise distances. So within the motive, all subsequences must be within a pairwise distance of 2r. Sadly, no algorithm was published. Let's look at the motivating example. We're going to use the song Rolling Stones painted black. If we look at the time series representation, it's the Mel frequency cepstrum coefficient of the song. Can you spot what is frequent within the song? Unfortunately, I cannot play it as I don't have the license. If we use state of the art and use a too small radius, we may find 6 occurrences of the same rhythmical section of a length of 3 seconds. Here highlighted are the lyrics of it. If you play it, you can actually notice that the rhythmical section is identical. Also depicted at the bottom is the actual motive that was found with 6 occurrences. If we now increase the radius r to a larger value and also increase the window length to 4.3 seconds, we may find a larger motive and also more occurrences. The question that arises, when are we actually confident we found all occurrences of the motive? We believe there are actually 2 problems in state of the art. The first one being distance is a real value and it's very hard to estimate by the user. If we set it too small, we may miss occurrences as depicted here. If we set it too large, we simply find everything as a motive. So the whole time series will be returned as a motive. And we can construct similar problems with the length of the time series as seen in the motivating example. Another problem is actually the hypersphere defined by a radius around the subsequences almost always overestimates the actual hypersphere of the top motive set. For example, look at the right. There are 2 motive sets of size 3 and both have the same radius. Yet the pairwise distance of both is different and the motive that has the smallest pairwise distance is the one on the right. This one is much more compact and has much larger similarity than the left one. Yet, for state-of-the-art definitions, both are equal. This comes to our novel algorithm, K-motiflets. K-motiflets is a motif set discovery algorithm. It finds K frequent motifs of smallest pairwise distance. For K equal to 2, this is actually equal to the pair motif discovery depicted here on the right. If we move from K equal to 2 to 3, we find the set of 3 time series. If we move to 4, we find the most similar set of 4 time series. This shape is also called Rayleigh polygon. Other than state-of-the-art, K-motiflets has 2 input parameters. One is the size of the desired motif set, and the other one is the length of the subsequence. Yet we have no radius or distance as input. How does it actually work? To find a K-motiflet, we input K as a parameter. Then we perform a KNN search around each of the subsequences of the time series, as depicted on the right. For each of these candidate sets, depicted in blue, red, and orange, we compute the maximum pairwise distance depicted below. So the maximum pairwise distance is the arc above, or is this distance, or it's equal to this distance. Finally, we minimize this pairwise distance over all candidate sets, and we call this maximum over pairwise distances the extent. The final most similar motif set is the red one, which is also the 3 motif. How can we actually learn K? Consider the following ECG trace. It consists of 2 motifs. In the left part, there's a calibration signal, and on the right side, there's an ECG signal. The actual motif is depicted on the top, so calibration signal and ECG wave. Roughly, there are 6 calibration signals and roughly 16 full ECG waves. How can we actually find the largest set of repeats for each of these motifs? Let's look at a geometric interpretation. If we slightly increase K from 2 to 6, we can see that also the extent slightly or linearly increases. So the 6 motiflet with smallest extent is depicted here in orange. Yet once we move to 7, K equal to 7, we see an increase in extent as we have to move from the orange motif to another motif which has a larger extent. The smallest 7 motiflet is depicted here in green. Yet again, if we increase K up to 16, we again see a linear slight increase in extent. Finally, once we move to 17, we see a sharp increase, which is equal to including this one subsequence to the other subsequences. When it comes to the algorithm, we can actually plot the size K against its extent. We increase K and look at the extent. In the first part, we see a slight increase in extent up to 6, which is mostly linear. Then up to 16, again, we see a linear increase in extent until we see a sharp increase afterwards. The elbows in this plot represent the largest meaningful motif sets, and a sharp increase indicates that we're either adding a dissimilar subsequence or we're moving to a different motif set. How can we actually find the best length of a motif? If we again look at this elbow plot, we are mostly interested in long flat stretches, which are equal to high numbers of repeats of the same motif. An ideal curve is mostly flat and has one sharp increase, one elbow at the end. We can measure this by the area under the elbow plot. If we plot for each possible length the area under the elbow plot, we get the following plot. And in this plot, minima correspond to long flat stretches. Here, for example, a heartbeat rate at 60 to 80 beats per minute. Let's see motiflets in action. First, we load the dataset, which contains calibration and heartbeats. Then we learn the length of the motif within a range of 25 to 200 data points. Here we see the area under the elbow plot, and minima in this plot correspond to a heartbeat rate of roughly 60 to 80 beats per minute. Finally, we can run the K-motiflet algorithm with the optimal window length. And this identifies the best motifs with the largest number of repeats. And here depicted are those motifs that are found: 6 repeats of the calibration signal and 16 repeats of the ECG wave. Let's get back to the motivating example. Human voice is represented by low frequency. We use the first MFCC coefficients from the wave file and search for K-motiflets. If we look at the area under the elbow plot, we can actually identify that the best motif length is around 5.4 seconds. Next, for this length, we compute elbows, and we find elbows at 4 and 10 repeats. And using 10 repeats, we can actually identify all occurrences of this rhythmical section, which is equal to "I see the girls walk by dressed in their summer clothes." We also argue that motiflets find better motifs. For that, we created a semi-synthetic benchmark with 25 time series with implanted motif sets. As we implanted the motif sets, we know the gold standard parameters, which we used as input to each method, like K for K-motiflets and the optimal radius for state-of-the-art. And as you can see to the right, motiflets outperform state-of-the-art by a large margin in precision. So motiflets mostly find the exact implanted motifs, while even given the optimal radius, other methods are not able to identify these. If we look into details, actually state-of-the-art often finds too small or too large motif sets. We measure the ratio here, like the optimal number, which can be found, and either they are 3 times higher or lower as the number of subsequences that can be found. And the reason is that the hypersphere defined by state-of-the-art always almost overestimates the actual hypersphere. There are many other real-world use cases in the paper with state-of-the-art competitors, and for all of these, K-motiflets performs better. Please see the paper and supporting website for details. Here's our conclusion. Many different motif set algorithms exist, and as central parameter, they all take the length of the motif and the distance threshold R as input. Yet we propose a novel algorithm, K-motiflet, which is the set of exactly K occurrences of a motif of length W. We argue that the value of K is mostly, almost always, easier to set than a distance value, and we introduce tools to automatically determine meaningful input values for K and for W. Also, we showed that motiflets produce better motifs than all competitors at lower runtimes. If you like to look at our source code and examples, please scan the QR code. Thank you very much.